Good evening, everyone. Welcome and thank you so much for joining us tonight. My name is Christine Muir. I am the community librarian at Cary Library. All of the programming at the library is made possible by the Cary Memorial Library Foundation, so we thank them for their work in supporting us. I am recording tonight's program and will be posting it to the library's YouTube channel later this evening. Everyone who registered will get a link to that video and you can share it with whomever you like. Zoom now offers closed captioning, and so I am going to enable that right now. If you find it distracting to see the subtitles, you can click on the live transcript button and hide subtitles. We will have time for questions at the end of the program. If you have a question, please use the Q&A button to enter that. If you put it into chat, I will ask you to move it over to Q&A because it's easier for our speaker to keep track of what's been answered using just the one space. Tonight's program is part of our series on science and economics, which we have been running for the past few years now. It is my distinct honor and pleasure to work with Mr. George Burnell on these programs, which happen a few times a year and always feature really interesting speakers on a variety of topics. I will now turn the virtual microphone over to George to introduce our speaker tonight.
Good evening. Welcome to the Cary Library Distinguished Science Series. Our speaker this evening, Sara Seager, Professor of Planetary Science, Physics, and Aeronautics at the Massachusetts Institute of Technology. She received her Bachelor of Science in Math and Physics from the University of Toronto and doctorate in astronomy from Harvard University, where she investigated recombination in the early universe before moving to the then brand new field of exoplanets. Professor Seager was a long-term member at the Institute for Advanced Study in Princeton, New Jersey. She's a senior research staff member at the Carnegie Institution in Washington before joining the M.I.T. faculty in 2007. Sara Seager's past research is credited with laying a foundation for the field of exoplanet atmosphere. Professor Seager works on space missions for planetary discovery and exploration. She was the Deputy Science Director for the MIT-led NASA mission TESS, PI for the on-orbit MIT CubeSat ASTERIA, and as lead for Starshade Rendezvous Mission, a space-based mission concept under technology development for direct imaging discovery and characterization of Earth analog. She leads a mission concept study for the search for signs of life or life itself in the Venus atmosphere. Sara Seager's current research interests are focused upon the discovery and characterization of exoplanets. She has two main goals: the discovery of another Earth and the search for signs of life by way of atmospheric biosignature gases. Thousands of exoplanets are known to exist with the exoplanet atmosphere, a firmly established field of research. Exoplanet observations are, however, mostly limited to giant exoplanets with puffy atmospheres. Seager's group aims to understand the atmospheric composition and the interior structure of small rocky exoplanets of the kind with the potential to host life. We are so pleased to have you join us this evening. I give you Professor Seager, your neighbor and mine.
Thank you so much for welcoming me. I'm going to share my screen now and get started. All right. Can you all see my screen? Well, I'm here to talk about exoplanets and the search for habitable worlds. Let me just jump right in here. So a few billion years ago, something amazing happened on our planet Earth. This humble bacteria, cyanobacteria, discovered how to capture energy by photosynthesis. And as a waste byproduct, these cyanobacteria produced oxygen gas. And eventually, over billions of years, our atmosphere became filled with oxygen to about 20% by volume. And what's so amazing about this is without these cyanobacteria and without what later became vegetation, without photosynthesis, our planet Earth would have almost no oxygen. So that's what we're trying to do, is we're trying to look at other planets and look for oxygen or other gases in the atmosphere. And, it turns out that every star in the sky is a sun. And there are so many stars. I mean, from here, Lexington, Concord, we can't see too many stars. But if you go to a truly dark sky, you can see many, many hundred, if not a few thousand stars. And in our own Milky Way galaxy, there are billions and billions of stars. And if our sun has planets, Mercury, Venus, Earth, Mars, etc., it makes sense that other stars should have planets also, and they do. And we call those exoplanets. So, when I look at the stars at night, I like to think about if there might be a planet around one of those stars, and if there might be intelligent life on those distant planets, looking back at our Earth. And the funny thing is if the life out there has the kind of telescopes we're trying to build, they're actually going to see our planet Earth, and they will see oxygen in our atmosphere. And they will think that, wow, something is really, really weird about that planet, because oxygen is so reactive. It's such a reactive gas, it shouldn't be in the atmosphere. And these aliens might be able to put everything together and suspect that there's some kind of life on our planet Earth. So that's what we're trying to do. We're trying to look for planets around other stars, and we're trying to study their atmospheres and look for signs of life by way of gases that don't belong. So just one more thing in this brief introduction is that a number of years ago, it says here 2007, I came across this booklet. And this booklet was about looking for life actually in our solar system, not on Mars or Jupiter's icy moons or somewhere else in our solar system. And I was really wowed by this quote. Nothing would be more tragic in the exploration of space than to encounter alien life and fail to recognize it. And why? Because although our Earth has oxygen, and that is an amazing gas made by life here, that we didn't always have oxygen. Our Earth has been around for 4.5 billion years. And we had oxygen for about 1 billion years, which might seem like a long time, but it really pushed me for my research career, which a good part of that is thinking through all the different gases that might be produced by life on another world. So what I'm going to do today in my talk is I'm going to walk you through the questions and answers, the questions that I get asked most often. And I get asked these questions by people of all walks of life. And these are, out of all of these questions, by the way, you can mull over, you can think about which is the one I get asked most often. And when I get to that question, I'll let you know which one it is. So the first question is, what is an exoplanet? Well, let me, before I define it for you, take you through a series of these so-called travel posters that NASA created. And these planets, these travel posters, we're not expecting to ever get to travel to another planet, but they're here to kind of just illustrate the kind of exoplanets that we found. This one says Kepler 186f, where the grass is always redder on the other side. And here you see two astronauts looking at a forest that is red. And the thought is that on some planets orbiting other stars, there are some stars out there that are far smaller and redder than our sun. And in this particular case, they're imagining that the life there that absorbs sunlight to harness energy, the pigments are just a different color. So they're imagining a red forest. Here's a poster that says, experience the gravity of HG 40307G. That's a real name of a real planet. a super-Earth. This planet is more massive and slightly larger than Earth. It has a higher gravity, so they're imagining what it might be like to go to a planet like that and parachute in its high gravity. Relax on Kepler 16b, the land of two suns, where your shadow always has company. And Kepler 16b is a planet that actually does orbit two stars. We call it a circumbinary planet. And what I like about this one is I love to say that science fiction got some things right. Here's a picture of Tatooine, Star Wars, where there are two sunsets, because this planet is orbiting two stars. This fictitious planet is orbiting two stars, just like Kepler 16b. Well, an exoplanet is a planet orbiting a star other than our sun. And for the more graphically minded, I put this slide in. You don't have to understand these plots to understand the rest of the talk. But I wanted to try to quantitatively capture for you just how many planets there are that we know about already. And if you look at this figure on the left, it's showing you planet mass versus planet orbital period. And each of the points on this plot represent a different planet. So you can see there's so many planets. In fact, there's a few thousand. They didn't all make it on this plot. And each colored dot represents a different planet finding technique. I'm going to go through a couple of them today. And what you're supposed to see on these plots is that, wow, the planets are literally everywhere. And so the planets come in many different masses, from about the same mass as Earth to 10, 100, 1,000, even, thousands of times, many thousands of times more massive than Earth. And some planets have, Earth is here, by the way, Earth, our time to go around our sun is 1 year, 365 days. Well, there are some planets that are showing up in the left corner of this plot where their time to go around their sun is actually less than 1 day. Their year is less than 1 day. There's some planets out there that are 2 to 3 times the size of Earth. They're way smaller than Neptune, but way bigger than Earth. And they appear to be the most common planet in our galaxy. We call them mini Neptunes, but they have no solar system counterpart. There's all kinds of planets out there. We don't know a lot about them. We know their planet mass and their size, but we don't know that much about them. We're trying to find more. So what is an exoplanet? We can define that as a planet that orbits a star other than the sun. Thousands of exoplanets are known to exist, but honestly, we expect that there are trillions of planets in our galaxy alone. That was the first question. So in having a conversation with someone, they usually move pretty quickly to the next question, which is, when will we find another Earth? It's very science fiction-y, People want to think of it like the movies, like there's going to be a planet we might get to study in detail or go there someday. Well, when we think about finding another planet like Earth, it's not like Earth is not fainter than the faintest galaxies ever observed by the Hubble Space Telescope, for example. The problem in searching for another Earth is that an Earth is right next to a big, bright, massive star. Like our Earth specifically, compared to our sun, our Earth is 100 times smaller. Our Earth is 300,000 times less massive than our sun. And our Earth is 10 billion times fainter than our sun in reflected light. And the problem is we can't really, right now anyway, separate out the planet and star. So we have to try to find the planet with techniques that do not get rid of the star, but rather in the combined light of the planet-star system. And so while it wouldn't be too hard to find an isolated Earth, it's like the proverbial needle in the haystack trying to find a signal of a small planet amidst this big, bright, massive star. So if I were with you and you were in the audience, I would literally ask for a show of hands. I would say, pretend that you're going to take a year off, whatever it is that you spend your time on, and you're going to take a sabbatical trying to learn how to find other planets like Earth. Would you choose a method that involves planet size? Because there you're dealing with numbers like 1 part in 100, 1 part in 10,000. Would you choose a method that involves planet mass? Because there you're trying to disentangle a planet signal 300,000 times, let's say, fainter than its star. Or would you choose to work with planet brightness? In this case, it's insane. You'd have to deal with a number like 10 billion, a planet that's 10 billion times fainter than its star. Well, I don't know if you'd want to choose the easiest one, but in the field of exoplanets right now, finding a planet using its size is actually the main way that we find planets today. And what we do is we look for transiting planets, planets that go in front of the star, as seen from our telescopes. And on the top, you see an artist's conception of a sun-like star, because we don't spatially resolve any other stars like that other than our sun. And I'm going to actually show that movie one more time. You can see what we do see is on the bottom. We measure the brightness of a star as a function of time. And we look for a tiny drop in brightness that signals a planet going in front of its star. So we don't see a picture, we measure the graph on the bottom actually. And did you know that astronomers like around the globe, we actually can monitor tens of thousands or millions of stars at one time. And we have a way to monitor their brightness and to use like large computer programs to sift through the data. And for every single star to make what we call one of these light curves. I mean, honestly, a simple way to describe it is it would be like taking your phone and like taking a picture of the night sky, like over and over and over again. And then every frame, represents one brightness point. And then you'd literally be trying to plot the brightness of that star for every frame that you've taken, and then look for a drop in brightness that might signal a planet going in front of the star. And actually at MIT, where I'm a professor, we lead this NASA mission called TESS, Transiting Exoplanet Survey Satellite. In the top left, you can see an artist's conception. You see the spacecraft, and you can see the big solar panels, which collect energy from the sun and then go into the batteries to store and then later use power. You can see like a dish here, an antenna to communicate back with Earth. And inside here, you can't see, there are 4 lenses. They're about 10 centimeters in diameter, like 4 cameras with 10 centimeter diameter lenses. And these actually are all stacked together so we can look at a giant strip of the sky. We see a lot of the sky at one time. Think about the constellation Orion. It's like 4 Orions stacked on top of each other. And this field is about 24 by 90 degrees. And in the bottom left, it's just a tiny part of what the field of view is. And look how many stars you can see. And our computer programs, like here at MIT or NASA has our official pipeline of record, they literally take this image and many, many more like that, sequential images, and they make a brightness time series looking for a drop in brightness. And you see on the bottommost panel on the right, there's some real data for you, showing you the white points are the data taken with the TESS mission. The yellow points are what we call averaged or binned data. And the blue line it's a model fitting the data. And it would take like a course, like an undergraduate level course to explain all this to you, like where it comes from, what it means. But I just wanted you to know that finding planets this way, it's really very standard today. It's a very standard procedure. And it's actually quite a mature way to find planets. Now, when you find this drop in brightness, it's not necessarily a planet. It could be other things too, like 2 stars orbiting each other. It could be noise in the data. It could be a lot of other things. And so finding these transit light curves is only the first step. When we find something interesting, we call it a TESS object of interest. And it goes out to the community and the data is public. And then astronomers all around the globe work to follow up these light curves, and they follow up the planet to see if it's actually a planet, or if instead it might be a binary star or just nothing. So that's kind of largely how we find planets today. But in the search for another Earth, we make it even one step easier than what I described, because our Earth is 100 times smaller than our sun. And by the way, I forgot to mention this drop in brightness. It's related to the area of the planet compared to the area of the star. So it's actually a ratio of areas. Remember pi r squared? So if we square the radius, we get the area, pi r squared. And so actually, a true Earth twin, if we're looking for a true Earth twin, an Earth around a sun, that drop in brightness is a part in 10,000 because we had to square everything. And here I'm showing you a real image of our sun and a fake planet, fake Earth-sized planet. And that fake Earth-sized planet is this dot right here. And on the right side, I'm showing you another type of star. It's called a red dwarf star. And here, this particular star is like a fake artist conception, but I've plunked that same planet right down in front of that star. And look how much area that planet takes out of the star. Much more, right? Much more than the Earth-Sun case. In fact, in this case, the planet-to-star area ratio is 1 part in 100, making it way, way easier. And there's a bunch of other reasons why it's easier to find small planets around small stars. And so the whole search for another Earth, it's not about finding Earth twins, more about finding Earth cousins, planets around small red dwarf stars. So let me take you on a virtual trip to one of these planets orbiting a red dwarf star. Let's imagine we could hop in a spacecraft and somehow magically traverse the vast distances between stars and get to one of these other planets. Well, the artist's conception here, the artist made the sun or the star very large in the sky. And the reason is because these small red dwarf stars, they give off less energy than a sun-like star. So in order for a planet to be warm enough for life, warm enough for us to theoretically visit, the planet has to be much closer to the star. So I want you to imagine a campfire, a big, huge fire. You know, you have to stay quite far away or you'll be too hot. But now imagine like the red dwarf star analogy, a tiny fire. You have to stand like right up close to that fire to get any warmth. So if the planet's close to the star, this artist took that to mean that the star could be the sun, the star could be very, very big in the sky. What I love about these planets orbiting red dwarf stars is that, you know, they're so close to the star that tides, you know how here on Earth we have tides raised by our moon and we have the ocean tides? Well, due to strong tides raised by the star on the planet over time, over millions, tens of millions of years, the planet actually gets into a very favorable rotation state. It rotates 1 time for every time it orbits. Just like the moon, actually, the moon shows the same face to Earth at all times. It's also been dynamically evolved into this favorable energy state. And what that means, if we could visit this planet, actually what it means for the planet is one side is always in daylight and one side is always in night. So if we could visit this planet, well, we could choose, where would you go? Would you go to where it's always day? Or you could go where it's always night. I think the astronomers would want to go to where it's always night, where it's always dark and you can see the stars. Or imagine you could go to a part on the planet where the sun is literally almost always setting. Wow. Now the planet is so close to the star that by Kepler's third law, 1 year, the time it takes to go around the star would be quite short, like a couple of weeks or maybe a month or so. So every year would only last a month. A planet year there would be like a month here. So if there are any kids in the audience, you know, your birthday would literally be every month. Now, on second thought, maybe going to visit this planet wouldn't be such a great idea because these red dwarf stars give off flares, big flares. We wouldn't be able to just constantly be flipping out our phones because the high energy particles coming off these flares would destroy the electronics on our phone and ruin our phones. And with all this high energy radiation, what kind of sunscreen would we bring? Well, these M dwarf stars, they're very different and the planets are also very different. But we're here just trying to kind of look at the easiest things we can find right now because finding planets and studying their atmospheres is very, very challenging. I actually have one more thing to mention on this. Here is a real image of our sun taken by a satellite. And our sun looks very mottled because it's at a wavelength, a very special filter. And what you're seeing here is a flare, like a brightening of our sun and energy and coming off our sun. It's something called a coronal mass ejection. The sun like kind of twists and turns and its magnetic field gets all tangled. And occasionally, like in a burst, the lines straighten out and then energy is released. And this amazing event happened in the late 1850s, so over 150 years ago, is that a British astronomer named Carrington was observing the sun, observing sunspots actually. And he saw the sunspots brighten a little bit, or a lot, I guess, actually. And a day and a half later, our Earth became electrified. Apparently, here where we live, we could go outside at night, and the northern lights were so bright we could read a book by them. And the northern lights and southern lights extended almost to the equator. Back then, we didn't have a power grid, but apparently some telegraph lines caught fire. And what had happened was part of our sun had come off our sun, and that had a magnetic field embedded in it. And this little piece of our sun came hurtling towards Earth and took a day and a half to get here. And that little part of our sun with a magnetic field hit Earth's magnetic field and induced a current. And no one got hurt or anything, but it's actually really interesting that some of these M dwarf stars, they actually give off flares with that amount of energy, like once a week. It's like we haven't had a flare like that for 150 years, and we're hoping not to get one again. We might, we don't know. But imagine being on a planet or being a red dwarf star where they have that level of flare. You know, I always think about it like this, like here we used to get snow days, you know, for kids, like there'd be a giant snowstorm and everything shuts down for a while. I always imagine on a planet like this, you'd have like a flare day. Like they'd see a flare coming and then quickly everyone has to like go in the basement for a day and wait for it all to pass. So who knows, but I'm just saying that, trying to tell you how these planets, all planets are different. Planets around these M dwarf stars, we're not really sure what they're going to be like, but we're excited that we have the technology to study them. So how will we find another Earth? Well, we will fast track by searching stars for what I call Earth cousins instead of Earth twins. We'll use transits, the most favorable planet finding technique for small planets. And we'll do that for the most favorable kind of star, small stars. So kind of that's where the field is rapidly not just moving, but that's where it's focused right now. So if I just have a conversation with someone and I'm explaining them about my work, what they really want to know actually is, can we go there? Now, I think a lot of you might already know the answer to this question, but I want you to know that this is the question I get asked most often. And sometimes I'll explain the answer to someone, or in a talk, I'll give the answer. And then I actually get asked this question again, and sometimes a third time, because people are just so excited about this idea of being able to travel across space. And yeah. Well, the answer is that, you know, our nearest star is 24 trillion miles away. And our fastest spacecraft, traveling around 20 kilometers per second, would take nearly 70,000 years to reach the nearest star system if the spacecraft was traveling in the right direction. Like the Voyager spacecraft that were launched in the late 1970s, they have left our solar system and they're like well over 10 billion miles away. But that's nothing actually. Even though it's so amazing for us humans to have sent some piece of hardware that far out, it's really not anywhere near where it needs to be to reach another star actually. So right now we don't have any way to travel to another star. And so the answer to this question is, can we go there? The question, can we go there? The answer is not for now, actually. But you know what's really amazing about this field of exoplanets? Well, when I started working on exoplanets in the mid-1990s, we only knew of 1 or 2 or 3, or let's say 5 exoplanets. And people thought it was pretty crazy to work in this field because they didn't believe the planets were real, for one thing. There's like a healthy skepticism in science when someone finds something new and most of the rest of the community doesn't believe it. And it was this, wow, like people told me not to work in this field because it wasn't going anywhere. They thought, we can barely find planets. How are we ever going to study their atmospheres, which is my specialty? So what I love about exoplanets is that the line between what is considered crazy and not worthwhile, and the line between what is mainstream research, that line is constantly shifting. So what's really interesting is that today studying exoplanets is very mainstream. Nobody questions it. But thinking of traveling to another star system is still pretty crazy. But I wanted to tell you about a project that is shifting that line. a plan that is underway to develop technology, not for us humans to go to another star, but to send thousands of spacecraft zooming past the nearest planetary system. So let me spend a minute telling you about this amazing idea. And by the way, this idea is funded by a billionaire. It's funded at the level of $100 million to try to get this project going. It's actually not enough to send something to the nearest star, but it's enough to make this idea, push it towards feasibility. So this idea involves sending space chips, they call it, little tiny spacecraft, sending up thousands of them. And each of these space chips would deploy a solar sail of a couple of meters in diameter. And as soon as these thousands of space chips deployed their solar sail, a giant bank of lasers, shown on the left here, on the ground, at about 100 gigawatt power. That would be like the power of 1 billion 100-watt light bulbs, that these lasers would shine on the spacecraft, or the solar sails rather, and using something called, and they actually would use radiation pressure. It's kind of like, not like wind, but it's like with photons, putting pressure on these sails would accelerate the sails to a 20th the speed of light. And just like when so many baby turtles are born and they go out to the ocean, like we're not expecting all those turtles to survive. And that's why we would send thousands of these, because they wouldn't all make it. But out of these thousands of spacecraft, they would accelerate to 20% the speed of light. And they would take, even at that very, 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 very inconceivably fast speed, they would take 20 years to get to the nearest star system. And then they take about 4 years to beam the signal back. So can we go there? The answer is like, not yet, but people are working on ways to move the line towards this being like a mainstream discipline to figure out how we're going to send a probe to a nearby star. And by the way, assuming some of these solar sails make it to that nearest star, they don't have any way to slow down. So just be zooming by the star and planetary system and taking images of the planet and sending the data of those images back here to Earth. So can we go there? Not for now. And then the follow-up question I get asked is, well, if we can't go there, like why look? Why are we doing this at all? Yeah, I get that question a lot too. And the reason is because, well, first of all, I don't know if any of you have seen Star Trek. If you haven't seen the original Star Trek or one of the many Star Trek series, I definitely encourage you to, because it's a great show. Well, in this case of Star Trek, the Starship Enterprise had to travel vast distances at incredible speeds so that it could orbit a planet up close, right? So that Spock could use his planet analyzer and look down and see if a planet was habitable or inhabited. Well, if you tried to do like a TV series like that today, but with astronomers' life, like it would be very boring, honestly. We spend most of our time in front of our computers. We don't really go to the telescope anymore. Telescopes are big and complicated, and we typically use them remotely, like with the telescope operator, and we just be like at home or in our office, like working on our computer and then analyzing data. In fact, we use data like from the Hubble Space Telescope, for example. We use Hubble Space Telescope to study exoplanet atmospheres, hot giant planet atmospheres. I'm going to come back and talk about one of these in detail in a moment. So we use telescopes to study atmospheres, but what's very exciting here in astronomy is that there's a new telescope called the James Webb Space Telescope that will push down to smaller and smaller planets and has the capability to study atmospheres of small rocky planets. And those are the ones that we want to look at for signs of oxygen and other gases that might indicate life. Now, this telescope is going to launch this year in October 2021. And you can see this giant mirror. It's composed of these segments of mirrors. And this telescope is about 6.5 meters in diameter, which is far bigger than Hubble's 2.4 meter mirror diameter. Now, this telescope is so big, they didn't put like a big baffle around it. It's just kind of open to space. And so the light would hit the mirror, it would bounce to this secondary mirror and then down through here where there are instruments on the back side. Now, what you see down below on the bottom left here is you see a giant sun shield. It's tennis court size. And it has 5 layers. Each has a different woven pattern. So as it's blocking out the sunlight doesn't get absorbed by these layers and heat up and end up heating the telescope. So it's very special, very complex, and we're all very excited for this to launch. And over here, this is showing you the TESS mission. TESS is nowhere near the James Webb Space Telescope. We just put it here as kind of a joke, because if you ever use it like a telescope and go to a amateur astronomy gathering, if people have a decent sized telescope, they always have this tiny telescope attached to it called the finder scope, because you need that tiny telescope with its wider field of view to find planets, and then you zoom in on them with your more powerful telescope. Well, remember how I mentioned how TESS is finding planets? It's finding like a catalog of planets that the James Webb Space Telescope will be following up. So that's how we want to find study planet atmospheres, is using the James Webb Space Telescope. So I'm going to tell you now how we study atmospheres. I want you to first think about a rainbow. I hope everyone here has got to see a rainbow. Well, did you know if you looked at a rainbow very closely, you would actually see that some colors are missing? And here's a rainbow. This is of our sun, a solar spectrum it's called, where the sunlight is split up into its constituent colors. And look at how some of these pieces are missing. This is due to atoms in our sun's photosphere, our sun's atmosphere, and perhaps some in our own Earth's atmosphere. But every compound, every gas has its own special fingerprint, its own special set of lines. You can see some lines are really thin, some are really fat, and we can kind of decode a spectrum like this and tell what's in an exoplanet atmosphere. It's actually not that easy for exoplanets, but I wanted you to know that we need to get these so-called spectra to identify a planet as Earth-like, because our Earth and our planet Venus, you know, it's funny because if there is an intelligent civilization who can find planets, but not study their atmospheres, well, it turns out that Earth and Venus would look the same from afar, because Earth and Venus are about the same size, they're about the same mass. But if one could look at their atmospheres, one would know they're completely different planets. Our Earth is very, very hospitable for life, and our planet Venus has a massive carbon dioxide greenhouse atmosphere that makes the surface too hot for life of any kind. So we're trying to look for gases in atmospheres of planets far away. Gases like I mentioned, oxygen or methane, and we have a whole list of gases like nitrous oxide or methyl chloride. We have a giant list, and we're keeping our eyes peeled for these unusual gases that might signify life. So I wanted to take a moment and talk about something a little more complicated. And you don't have to understand this to understand the rest of my talk, but I wanted to give you something to sink your teeth into, let's say. So I wanted to explain to you how we actually observe exoplanet atmospheres. And what I'm showing you in this cartoon on the right, it's a planet, an artist's conception of a planet going in front of the star. And you see the planet in brown, kind of looks like a bit like Jupiter. But you see that this bright blue part of the atmosphere glowing around the planet, right? And what's interesting is the artist is trying to show you that some of the starlight shines through the atmosphere. So what I want you to think about, I want to explain to you how we think about planets when we observe their atmospheres. Well, first imagine for a moment, you're observing this planet go in front of its star at a wavelength where the atmosphere is completely transparent. Then the planet is a certain size, as you can see from this brown disk of the planet. Now I want you to imagine taking a measurement at a wavelength where the atmosphere is opaque. It's very strongly absorbing. Well, in this case, the planet looks a tiny, tiny bit bigger. And here you would be thinking about the size of not just the brown disk, but of that glowing blue atmosphere. So let's go over that again. At a wavelength where the atmosphere is not absorbing, we would see a planet of a certain size. And in a wavelength where the planet is highly absorbing, highly opaque, the planet actually looks a little bit bigger. So we're actually looking for, sounds kind of weird, but we're looking for a change in planet size as a function of wavelength, because the planet looks bigger where the atmosphere is absorbing. And what this plot is showing you is, you can think of this as planet size on the left. It's not quite planet size, but we'll think of it as planet size. And don't worry about the numbers or the scale right now. And on the bottom is the wavelength in microns. So 0.3, 0.4, 0.5, these are visible wavelengths. Out here at 1.52 microns, these are infrared wavelengths. Each of these white points with an error bar is taken by the Hubble Space Telescope. The far ones out here are by another telescope called the Spitzer Space Telescope. And these colors are models. They're computer models to make models of an exoplanet atmosphere. And what you can see here, I'm sure you'll agree with me that these points, these white points, they're different from a straight line. And in fact, because the points go up here, they go up, down, this planet actually looks a tiny, tiny bit bigger at certain wavelengths. And in fact, this planet looks a little tiny bit bigger right where water vapor has very strongly absorbing properties. And that's why it says H2O everywhere, because this model is showing you a lot of water. And wow, it's incredible, but this is detection of water vapor on an exoplanet. And this exoplanet is, we call it a hot Saturn. It's a big planet. It's very, very hot. It has like a giant puffy atmosphere. And it doesn't have a water ocean. It just has water vapor in the atmosphere because it has hydrogen, it has oxygen. I just wanted you to, enjoy this data. And again, to appreciate that it's different from a straight line, markedly different. And this is actually one of our very best exoplanet atmospheres. And we do have a few dozen of these. And we're really excited to see where the future takes us. And this signal, by the way, this is a very favorable one. It's about 1 part in 1,000. But when we're thinking of small rocky planets, the atmosphere is very thin. It's like the skin of an onion on an onion. And in those cases, the signals will be much, much smaller, much, much more difficult to untangle. So I want to just review the whole picture from the start. We're looking for planets. To make our lives easier, we're using the easiest technique, transiting planets. And when we find the transiting planets, our goal is to look at the atmosphere by looking for the way that the light shines through the atmosphere or doesn't make it through. And by analyzing the gases in the atmosphere, we're looking for gases that don't belong, gases like oxygen, that might ultimately indicate the presence of life. We have other telescopes besides the James Webb Space Telescope. I didn't have time to talk about them, but I just wanted to very briefly mention them. On the bottom right here, there's a picture of an artist's conception of the Giant Magellan Telescope. This is a huge telescope that each of the mirrors you see on it are 8 meters in diameter. And the effective diameter of them all together is 20 meters. The Europeans are building a 40-meter telescope, and there's another project in the United States that will be 30 meters. And these are huge, giant telescopes. You can see a truck down there for comparison, and it doesn't do it justice. You can see on the bottom left, there's a crazy concept called Starshade, where a giant specially shaped screen with its own spacecraft would formation fly with a space telescope, all in outer space, very far from Earth's gravity. And the starshade would block out the starlight, so we can study the planet light directly by itself. So there's so much work going on in exoplanets, so many threads moving forward. I just picked one concrete one to focus on for you today, but I wanted you to know there's a lot of work going on, and there is a way to observe planets with each of these different telescopes. So if we can't go there, why look? The answer to that question is we're doing remote sensing. We're using telescopes to find and study other planets, and eventually to search for signs of life by way of gases in the atmosphere. So I'm going to summarize now. Exoplanets and the search for habitable worlds. What is an exoplanet? It's a planet that orbits a star other than the sun. My main takeaway for you today was, when and how will we find another Earth? The main takeaway is that we're taking this fast track. We're searching for small planets transiting small stars. And can we go there? Not for now. If we can't go there, why look? Remote sensing to search for water vapor and signs of life in small rocky planet atmospheres. And all I can say now is, stay tuned. This field is rapidly developing. Once our new telescope launches, we'll be having many exciting results in this field. Thank you very much for your attention tonight. I'm going to stop sharing my screen in a moment, and we have some time for questions. So I'll start by answering your questions. You can put them all in the Q&A. All right, so let's see. Yes, there's a question from Tony, and he answers his own question. He says, if an exoplanet orbits in less than 1 day, wouldn't it be too hot to support life? And the answer is yes. There's planets, most of the ones we find, honestly, are way too hot to support life of any kind. They're either too big or too hot. The planets that can host life, they're hard for us to find, and we don't have that many of them. There's another question from Walt. What is Planet X? Well, Planet X, it kind of is a planet, like people always want to imagine there's another planet in our solar system that we haven't found yet. And it's always called Planet X. And Planet X is always some mysterious planet. Maybe it kind of messed up our asteroid belt and killed the dinosaurs. It's usually something bad. Right now, there's a planet called Planet 9, which Planet 9, which is kind of like a Planet X. We haven't found it yet, but people see evidence for Planet 9 because we have some dwarf planets, some like Pluto and many other planets far, far away from us here that have strange orbits in the sky. And people think there's a Planet 9 kind of shepherding those planets along, but we haven't found it yet. So Planet X is still a possibility. We have question from Boston. What is the latest on the Drake equation? Well, the Drake equation tries to illustrate for us on the topic of the search for extraterrestrial intelligence, specifically those that have the ability to communicate with us by radio waves. And there's a big program still going on called SETI, Search for Extraterrestrial Intelligence. And we're listening in with big radio telescopes. We're kind of hoping that there are intelligent aliens trying to send us a message, and that we'll be looking in at the right time. So far, we haven't found anything, but the experts say that we've hardly searched. We've only really searched the equivalent of like one glass of water compared to the entire ocean. So we're still listening in on that. Question from Joe. What are some atmospheres are alternative to oxygen that you think might support life? Well, remember, oxygen supports our life, our human complex life, but oxygen is a waste byproduct. So we're assuming that life elsewhere, like we do, also uses chemistry, and that life has waste gases that accumulate in an atmosphere. So we have a huge list of gases. I could list a few for you. We have gases like methane, gases like phosphine. There are some gases like methyl chloride. There's kind of a long list, and they're partially based on gases made by life on Earth. Now, many of these gases are kind of confused because methane, for example, is made by life, but it also comes out of mid-ocean ridges. Like it's also a gas produced by geology on Earth. So the field is really quite complicated, and there's a lot of gases that are made by life, but many of these gases also are made by volcanoes and other things. So we don't have any really unique answers in that question. How can we follow along for updates on research in this field, such as future missions? IG, the Mars rovers have Twitter accounts. Yes, well, there's really no one source, but if you do start following like major observatories, like you could follow, I think you just have to do some digging. But if you're on Twitter, there's plenty of stuff out there. You just have to do some digging. And you know how once you follow one, you get automatic suggestions to follow others. Like you could follow European Southern Observatory, for example. All the big astronomy observatories have Twitter accounts and announce discoveries when they come up. You could follow the TESS mission, for one. What did the Kepler spacecraft find? Well, NASA's Kepler telescope was the first telescope dedicated for exoplanets. And Kepler was a very special telescope. I actually was at the Kepler launch, the rocket launch, back in 2009 from Cape Canaveral, Florida. And it was a spectacular launch. It was a night launch, and the sky was so dark, and the rocket like launched perfectly, and the solid rocket boosters were hot and glowing, and they fell off into the ocean where they would later be recovered. It was a great evening. Well, Kepler actually stared at one part of the sky for 4 years. And Kepler's its original goal was to find how common are Earth-sized planets orbiting Earth, sun-like stars, that is Earth-like planets and Earth-like orbits. But instead, Kepler found an incredible wealth of planets that we had never imagined. You know, those planets that are so close to the star that they orbit in less than 1 day, they're so hot that the sun heating their surfaces, we think it's hot enough to melt rock. That's not rock from volcanoes, but just melted rock from the power of the solar heating. Kepler found this amazing thing. It found that planets 2 to 3 times the size of Earth appear to be the most common planet in our galaxy. They appear to be more common than Jupiter-sized planets. Yet we have no solar system counterpart, and we have no idea so far. We don't know what they're made of, how they formed, or why they're even there. Like we thought that planet formation, we thought that Jupiters would be extremely common, that planets start forming, and like a cosmic vacuum cleaner, once they get big enough, they suck in all the material from their feeding zone, and they grow and grow and grow until they've exhausted their supply. Well, it turns out that that's apparently not what happens. That's apparently not the most common way for planets to form, because all these small planets, 2 to 3 times the size of Earth, yeah, we don't really understand them. And that was one of Kepler's biggest findings. But honestly, Kepler found thousands of planets. It really changed the field immeasurably. Someone asked about the MacArthur Fellowship. Would you be kind enough to share something about what research this award enabled you to do? Well, I'd say it's 2 things, because the MacArthur is a huge amount of money. It was like $600,000, and it comes out over 5 years. And you can literally do whatever you want with the money. In my case, believe it or not, I had to just use that money for home childcare. I had, at the time, unfortunately, a terrible thing happened to my family. I became widowed. And literally just to work, like in case you don't know this, but for women to work, or like someone has to do all that other stuff. And so I literally had to spend that money, like after tax, just on household help and just various things. And it was like a lifesaver for me, because it's really hard to do this job and be consuming job where I need to dedicate all my mind to it without having like someone else to help out in a major way. But the other thing was funny about the award, which because like, you know, we can each believe in ourselves. Like, I believe I'm on the right path. I believe this, but somehow the rest of the world might not fully believe. And so what the MacArthur really enabled in a way was it enabled me to carry a lot of my bold ideas forward, because the other people somehow had to have like this stamp that helped them believe. So the MacArthur was really, really, really enabling, actually. And I just wanted to share with you 2 funny things with it. So one of it was, when you get this award, it's all very secretive, and you don't know that you're even in the running for it, actually. And so you get like a phone call completely out of the blue, and they're like, "Oh, are you sitting down?" But when my phone call came, I don't answer my phone, because I don't like the telemarketers on my mobile, but at work, I think the only people who call me are people who have like UFO stories, and I don't believe in UFOs. And it's hard to talk to people who just want to share their story with you. You know, like one time, this woman called me over and over again. Like I didn't know who it was. Some person wouldn't stop calling. Like on the 10th time, I thought, okay, I just better pick this up and let them know to stop calling. And this poor woman was like just beside herself with anxiety and worry. I mean, clearly she had other problems than her supposed view of the UFO. But I just calmly explained to her, like, I'm not able to help her on that. And then she just paused and she's like, "Oh, okay." And then she hung up and never called me again. So like, because of all of that, I don't answer my phone. But at the time I had an assistant, Derek, and he answered the phone, and someone called, but they wouldn't tell him why. And it was actually the MacArthur Foundation. And he got the call, and it sounded very suspicious to him. It sounded like one of the UFO callers. And so he told them, no, they couldn't talk to me, actually, because no, thank you. And that was that. And so a bit later, I received an email, and it was very good. It was just said, "Oh, you're very wonderful and protective assistant wasn't able to let us through. Can we call you?" And I was like, wow, this is wow. And I wasn't sure why they were calling, of course, because in previous years, I have been called upon to evaluate other nominees. So I thought, well, maybe they're just calling to ask my opinion on another nominee, or maybe it's my lucky day. And so the next day I called, and yeah, that was the story. All right. Although difficult to study now, why not try to study planets orbiting suns with the same luminosity as our sun, hoping to find a planet similar to ours as we know it? And thank you for asking that, because that is my dream. I really want to do that. And the reason we're not doing it is because planets are so small compared to their big, bright, massive star. And it's incredibly hard to find another Earth. People are trying. Honestly, people have dedicated telescopes, dedicated programs. But the way that we really want to do this, it's just very challenging and very, very expensive. I'm going to take this moment, since you asked, to share part of my talk that I didn't have time to go through. It'll just take me a couple of minutes here. Okay, I've got to scroll through all this now, so just hold on here. Some of this you've seen already. Okay, I actually had a part 2 to this question, but it takes too long to explain, so I'm going to give you a shortened version. And this is to answer Dick's question. We want to do that, and I'm going to tell you a way that we want to do. It turns out these transiting planets are the first part of a long story, because they're limited to planets that are just right aligned, fortuitously aligned. If a planet is orbiting its star in the plane of the night sky, it would never show a transit. So we're actually missing a lot of planets out there. And yeah, so what we want to be able to do is to send up a giant screen to block out the starlight so we can see planets directly. And for a variety of reasons, this might be our best way to find another Earth, actually, is to go to space and block out starlight just so we can find all the planets, like Earth, like Jupiter, like anything. And we actually do have a project, an idea that was conceived of in the 1960s and has been revisited every decade since until now. We actually think we can actually build this. And this project is called Starshade. Oh, right, I forgot to mention, okay, so we could put up a giant circular shaped screen to block out a point source, a point of light. But unfortunately, even if we did that, we wouldn't block out the light entirely, because light can act like a wave, and it can actually bend around the edges. It would actually bend around the edges of a giant circular screen, and it would create this pattern you see on the right called an airy ring pattern, where the ripples of light are larger than the planet signal we'd be looking for. It would be like dropping a pebble in a pond. You'd see ripples. And the actual shape has to do with a very special mathematical design. You can see here one design on the bottom left. And in that case, if we could block out starlight, a point source of light, it would diffract, it would bend around the edges of this special pattern in such a way to cancel out itself, leaving an image that is very, very, very dark. It would be like dropping a pebble in a pond, and instead of seeing ripples, that pond would be perfectly smooth, and all the waves would be pushed to the outside edges. So people have been working on the Starshade for a long time. Here's an animation showing you a Starshade launching together with a space telescope. Those petals would unfurl from their stowed position, and this truss would come out, snapping those petals into place. This whole thing has to be incredibly precisely engineered. Starshade would have its own spacecraft. It would formation fly with the telescope. The goal ultimately to be blocking out that starlight so perfectly so that we could see the planets directly. And that animation comes from NASA. Now, this project is ongoing, but it's incredibly expensive. And the reason we're not doing it is really just cost and the will of the community. Here's myself and 2 team members with a real petal from Starshade out at the Jet Propulsion Laboratory in California. And this one was made, look at the very sharp tip here, and it's got really special edges. It was made to show that people can manufacture that Starshade to within the exact specified shape. And here's one more picture of Starshade, a lab, again, same place. And here you can see small scale versions of the Starshade, figuring out how it would stow and deploy and things like that. So we're trying to do that in parallel, but it's moving very slowly, trying to find planets around sun-like stars, planets like Earth, but it's just challenging because of the numbers and the complexity. Okay, here's another question from Steve asking, planets going around other suns, are they all in the same plane like our solar system? So just for those who don't know, most of our planets, they're orbiting almost in a plane. And the answer is most appear to be, as far as we can tell, most appear to be orbiting in the same plane, but some of them are definitely not actually. It turns out there are some planets very close to the star, giant planets. They're actually orbiting pole on. And Yeah, they must have had some crazy interactions with other planets or other stars to get in that form. So for the close-in planets, a number of them seem to have very strange non-planar orbits, but other planets appear to all be in the same, many of the other systems appear to have planets in the same plane. How big is the Starshade, right? I forgot to say. Okay, we have a lot of different versions of Starshade because we're trying to sell to the community, to NASA. And we have big, expensive ones and smaller, still expensive, but cheaper ones. But the Starshade is typically tens of meters. So like our ideal Starshade is probably 40 meters in diameter. We have a version that's more like 26 meters, that's more manageable just in terms of building it and stowing it. And that actually gets us to the end of our questions. So I'll just, perhaps I'll turn it back to Christine and we can still just wait a minute and see if any more questions pop up.
That would be fantastic if you still have a minute. I think one more did just pop in. How far away from the Earth?
Well, the key is to get away from Earth, only because Earth's gravity makes the very, very special formation flying very complicated. And the place that astronomers like to send their telescopes now, it's like an Earth-Sun balance point called Lagrangian point number 2. And it is about, it's like over 1 million miles away from Earth. So it's very far away. But the James Webb Space Telescope is going there, and we've sent other space telescopes there. So that's where ideally we would send it.
I have a question that's not as much about the science, but while we give people one more minute to see if they have any other questions, you showed a lot of artist conceptions tonight, and I'm curious to know how the artists come up with those. Do scientists weigh in with some sense of what it could be based on some data, or how do they come up with that?
Yeah, sometimes they do. Like the posters at the beginning, they're made by very conscientious artists, and they definitely ask scientists, what do you think of this? What do you think of that? Usually what we say is pretty boring and cut and dried, so they need to expand a little. Other times, I think the artist just comes up with it completely on their own, actually. So it's a bit of both, actually. Oftentimes, if a scientist makes a discovery, then you get to have an artist as part of the outreach team to be able to communicate it. And so a lot of the artwork comes from those kinds of past events.
It's kind of interesting to me because so much of your work is based on asking a lot of what if questions that kind of fall way outside the box. And yet a lot of times the art is something we can still relate to. So that balance of being sort of revolutionary and innovative versus relatable is kind of an interesting contrast, I think. I don't see any other questions in the chat. So I am going to ask George if he'd like to turn his camera back on and unmute himself as well. And I just want to say thank you to you, Professor, for joining us. And thank you to our audience for being here and for asking such great questions. This is a topic that Lexington loves, so we really appreciate your time and attention with us.
I marvel at your ability to wander through the stars. I can't find my way from Lexington to Concord. And it's very interesting. I don't know how much of this everyone else absorbs or has specific interest in, but for all of us, the exploration and the unknown and the marvels that are uncovered by the kind of research that you do certainly stirs the mind. And I thank you very much for bringing that knowledge and that inquiry to us. I'm sure that next month and the month after, people are going to be asking, either asking me questions or commenting on the material that you've presented. And we appreciate very much your being willing to share it with us, to enlighten us and broaden our horizons. You certainly have a horizon that's broader than our usual one. It's been a wonderful experience. We thank you very much, and we very much appreciate your willing to spend some time with us. Thank you.
You're welcome.
Thank you again, everyone. Have a great night.